So in module 3, we'll see the next topic, that is sorting large files from disk. So here mainly we'll be seeing about merge sort, and as we have seen in the previous section about sorting from memory, we have seen about key sort and its drawbacks. It was like it was very expensive to do sorting from the memory because maintaining an index file and then trying to sort the data file was very much expensive. And we had a second drawback, like if my index is very large, it was difficult to do use key sort algorithm. For this, we had gone for the next the solution for this problem was introducing merge sort. Okay, and here what is the main how is it done means we are trying to break um, we are trying to break our files into sub files known as runs. And then what we do means what is this runs done means we are going to retrieve each and every part of our main file as runs, and we'll sort each and every runs, and afterwards we'll put it as input to our merge sort. So now the merge sort will sort every run and output it to my disk. Okay, so this is what the merge sort works. So for looking into the advantage of merge sort, here we are having main two steps as I have already explained. The first one is reading the input, that is for a run creation step. That here the reading is sequential, and then the next one is we have to after reading we'll go for creating runs. That is, in the runs every data which is read has been sorted and saved as runs. Okay, so it is again written into the disk. Now we are going for the second stage where we are going to do the merging. In the merging case, now again what we have to do means we have to read the runs from the disk and give it as input for the merging. Once we do the merging, then what we have means we have the sorted files which is ready to be written to the disk. So after merging, we'll write the sorted list sequentially into my disk. Okay, so we can tell, or the only here in this throughout the sequence, the only place where we don't have sequential access is whenever we are going to switch from one run to another run. Here the technique which is used for accessing is we are using random access. So here we can end up with long seeking time, okay, because it is not sequential. Here we can tell that we can try to introduce overlapping of input output similar to our heap sort, so that we can improve the seek time. Okay, this is also being tried so that to improve the performance of our algorithm. So we can tell here we have tried to improve the performance by maximum concentrating on making our access sequential. So tapes can be used. So here this is how it looks like. Consider that I'm having 800,000 unsorted records. Here this has been it has been divided into 80 runs. In the sense, one run is having 100 bytes. Okay, so similarly for 80 runs it will be retrieving that much data, 100 bytes, and for every 100 for each run it requires 80 seek for reading the whole data into one run. Okay, and then once each and every runs are available, each and every runs will be sorting the data and saving it inside the disk. So here the disk is being written with the 80 runs. Now what do means we do merge sort by reading again from the disk the sorted subfiles or the runs are being read from here, and it is given for merging. Now when we do the merging, the sorted files or the sorted runs are being written into my disk, and we get the 800,000 records in a sorted order. So this is how my algorithm works. So we'll see it step by step. We can tell now the procedure is divided into two phases, that is sort phase, and the second phase is merge phase. Okay, so since we have seen that we have to mainly try to improve our performance. We try to improve our performance by telling that our seeks are always done by using sequential access, and the only thing which is addition is for every seek we have an rotational delay similarly, and for that is for every axis. Here now in sort phase we have many two steps, that is reading the data from the disk into the memory, and then we do sorting, and after doing sorting we save it into runs. Okay, so this is the first step. Second step is after the run is written, we have to write the runs into my disk. Then comes to the third step, that is in the merge phase. In the merge phase, we have two steps, that is reading the input or the reading the runs from the disk into the memory. And this runs are given to the merging as input. Once it is given for the merging phase for input, now the next step is writing. The merged data need to be written to the disk. So that is the fourth step, that is writing the data into the disk. So these are the main four steps. We'll see each by each so that we'll understand the algorithm. So the first step is, as I have already explained, it is reading the data from disk to memory. Then we'll sort it and write it to as runs. So here we are considering that our memory is having 10 megabytes of chunks. Okay, here, so one file is having this much of data. Now we are going to see how is it been splitted up. Now this data is splitted into 80 runs. Okay, now 80 times for reading 80 runs, each run have to be read 80 times, so that the run has been completed. Okay, so we can tell it is 80 seek time. Okay, we'll see the calculation so that it is understandable. Now for calculating the time it takes to access each block means each run, it is seek time plus rotational delay, seek time plus rotational delay plus the amount of time it takes to transfer the data or the transfer the block. So we can tell if seek time is equal to 8 millisecond and rotational delay is equal to 3 millisecond, we can tell the time of seeking is 11 milliseconds. Now we need to know what is the transmission rate. The transmission rate is 14,500 bytes per millisecond. So we can tell the total input time taken to read in the sort phase, that is 80 seeks for 800 megabytes of data. It is access time is 80 seek into the seek time. 80 seek into the seek time. Seek time is nothing but 11 milliseconds, that is equal to 1 second. And the transfer time means the 800 megabytes of data into the transmission time, that is equal to 60 seconds. So the total input time of your sort phase is 61 seconds. Next, write sorting runs to disk. So the sorted runs are written to disk. Now we need to know what is the time taken for writing it into the disk. It is similar to your reading phase. So we can tell it takes the same number of seeks as reading, and it takes the same number of data transfer similar to your reading. So we can tell, as in the previous step, the same time is taken for writing as well. So it is 61 seconds. The next one is, next step is reading sorted runs to memory for merging. Okay, now when we read the data from the disk to give it for merging, what are the time taken, what are the steps? Okay, here as usual the same time it is taken as in the memory. We are having 10 megabytes of data. Now we are dividing the 80 parts. Our data is being divided into 80 parts, so that every 80 part is given a buffer from the memory. The memory is having 10 megabytes of data. So now 80 parts, so that we can now tell that we are having 80 runs. Now our data is divided into 80 runs. Okay, now each runs are read by one seek. Okay, so here in 80 input buffers, we are having 80 buffers hold 1 by nth of the run. So one seek, only 1 by 80th of the run has been read. Okay, so for reading 80 for reading one whole run, we need to read it 80 times. So that is why it is written 80 buffer holds 1 by nth of the run. So that is why we have the calculation time of seeking 80 runs. The time taken is 80 runs into 86. For completing one complete run, we need to read it 80 times, because it holds only 1 by 80th of the data. Okay, so the total time taken is 6400 seeks. Now the total time taken, that is, it includes the seek and the rotation. As we have already discussed, for every one seek the rotation time is also 1. So here we need to calculate both. So it is equal to 64,000 into 11 millisecond. Previously we have seen the seek time is 11 millisecond, so that is equal to 70 seconds. Now we need to know the transfer rate. So as similar as what we have seen in the previous step, the transfer rate of 800 megabytes is equal to the same. It is the same here also. The transfer time is 60 seconds. So this is how it looks like. The first run is equal to 80 buffers. So for every seek, only one buffer is read. So that is why for every run, 80 seeks is required. That is why we get 80 into 80. Okay, 80 buffers into 80 times. Okay, that once 80 times 80 accesses is done, then we get our whole run completed, reading completed. So this is how, and afterwards we get the sorted array after the merging and all. Okay, now the last step is how do we write the data. Okay, for writing the data again we need to need output buffer. It remains the same. Now consider that we are having 200,000 byte of output buffers. In that case, how many times or how many seek is required to write the data? So in that case, I'm having 800 megabytes of data, and I need to know if I'm given a 200,000 bytes of output buffer, how many seeks is required to write the data. It is equal to 400, okay, 40,000 seeks. Okay, so we can it is not 4, okay, so we need how many seeks? 4,000 seeks. Okay, here, so the total seek and rotational time is 4,000 into 11 milliseconds, because the seek time and rotational time is 11 milliseconds. So it is 4,000 into 11 milliseconds, that is equal to 44 seconds. And as before, the transfer time again remains the same, that is 60 seconds. Thank you.